Fernando, hi.
How are you? Can you hear me well?
Can't hear you.
Oh.
My fault. Try again.
Hello.
Good to see you. How are you?
Pretty good, thanks.
Okay.
Enjoying our winter time.
Yeah, looks nice there. I have one slide to introduce you, and then I'll share my screen for that slide, and then say 90 seconds of introduction, and then pass along to you. Okay?
Fine.
As we agreed, 15 minutes. I'll give you a 5-minute warning.
Perfect.
And I'll say a few words to the people who join us before we start about how we'll handle questions, I think.
Okay. Yeah, it's a little bit of a pity that it's not possible to activate microphones or anything like that. Everything has to be through this chat or Q&A system.
I'm not sure about that. We'll try it. I've had, as I said in my email a while ago this morning, I've been in quite a few sessions already, and it's been disappointing to me that the questions have not been Well, we are at time here. It's 11:30 East Coast US time, which I believe is our nominal start time. So let me welcome everybody that's joined the session. We have 62, 63, 64, it's going up, a number of participants. Our speaker is here. Let me open by procedural points that I'm chairing the session, and I would like people, if they want to ask questions, to put them in the chat for everybody to see. We will not have questions until the end of the talk, and then I'll select, depending on how many we have, I'll take the chair's prerogative to select the questions. But we do hope to have some questions and to find time at the end for questions. That said, I'm delighted to be here as chair of the foundational lecture today. And to introduce Professor Quintana, Fernando Quintana, senior Bayesian, a distinguished statistician and a good friend. So most of you will know that Fernando is a major player and has been for a number of decades, a senior leader in our profession, who's made many distinguished contributions to Bayesian theory and methods generally. One of the areas, but perhaps particularly, he is noted for pioneering research in Bayesian nonparametrics. Fernando, those of you that know him and have read his papers will know he's a very deep thinker in terms of the conceptual and theoretical bases of our discipline. And that really is a key point for why he is here today giving a foundational lecture. Fernando has served ISBA in many capacities. He's been a leader of the profession in Central South American section development, and particularly notable for his work in the nonparametric Bayes section, BMP as we call it, arguably ISBA's most active and vibrant section for a number of years. Fernando is the current past chair of the BMP section. In respect of his work and recognizing his work and his stature in the profession, and particularly in Bayesian statistics, Fernando was elected as an ISBA Fellow last year, 2020. And that honor is now complemented by what I regard as ISBA's most distinguished speaking awards. He is presenting one of today's lectures on what we used to call Bayesian foundations, but in recent years, we've been calling that the foundational lecture. So I'm delighted to introduce Fernando and hope that you will join me in congratulating him on his achievements generally, but also on the recognition and selection as a foundational lecturer today. I think we can all expect to enjoy and learn from what Fernando has to say to us today. So with that, I'll stop my share and invite Fernando to share his slides and kick us off.
Okay. So First of all, let me see. Can you see my screen?
Yes.
Can you see me moving it?
Perfect.
Okay, thank you very much. Well, thank you. Thanks a lot, Mike, for the very kind introduction. I have to say that Alicia mentioned 2 days ago in this on her foundational lecture that it is an honor to be here, and I agree with that. Wes repeated that, and I think I will follow suit. But I have to say also that me being here is also because of the people I have worked with, and I deeply thank them all for being my collaborators and ultimately my friends. I call them my friends. So anyway, this is my way of introduction. So I'm going to be speaking about random partition models. This is the kind of thing I've been doing mostly over the last years. So a little bit of the outline of this talk. I'm going to give some background, mostly to introduce notation and to give you a kind of like a biased version of how I became interested in these things and some of the latest developments, not done by me only, of course. I'm going to be doing a little bit of a review. And then I have 3 further things to discuss regarding applications of random partition models. If I don't have time to go through all of them, that's fine, but that my ambitious plan for today is to go through all of that. So, okay, so some background. This is like I said there, is a very biased description, but first of all, I need some notation, okay? So the notation I'm going to be using is this square bracket n is just a set of indices. So that those are the things that you are to work with. And a partition of that is just a division of this collection of indices into Kn. The sub-index n, of course, is because of that depends on the size of the population. And the partition is supposed to be into mutually exclusive and non-empty subsets, okay? So the Pn over here is the set of all partitions, and of course there's lots of them. The Bell number is the one that describes the number of partitions. So with I don't know, there is with 5 individuals you have 52, and with 100 you have all this huge number over there. I cannot even say it. Right. Okay. So partitions are also typically represented by class memberships, and this is a typical trick that we all use in this world. So identifying the class memberships, and then you can go back and forth between partitions and these class memberships indicators. All right. So and the other thing is that we typically have measurements and covariates. So the y's would be our responses, the x's will be the covariates, and whenever you see a star over here, I'm referring to individuals that belong to a certain subset. The j is the index of the subset. Okay. Now, a random partition model is simply a distribution, in my conception now. It's a distribution on the collection of all possible partitions of our index set. The way I came to this world is through Bayesian nonparametrics. So if you consider what I call here prototypical BMP hierarchical model, that means that you have your observations over here and certain parameters, and you assume conditional independence. And then the next step in this hierarchy is to say that these parameters are drawn from a certain distribution, and the distribution is a member of a large class of distributions called discrete random probability measures. For instance, here is one generic member of the class. It's just a mixture of atoms drawn in some way and with some weights. And of course, to make this a valid probability model, you have to have that these weights add up to 1 with probability 1. Okay, so the main thing here is that this is a discrete random measure, which is a mixture of course, in this way. And because of that, a sample from that distribution means that there's going to be ties among these theta values. If again use the star notation to indicate the unique values, then a partition can be induced by looking at the set of parameters that match some of these unique values. If you assume that the parameters, these unique values are drawn from a non-atomic measure, which is typically the case, you will have that these things are all different with probability 1, and therefore you define a partition in that fashion, just by looking at who matches what. All right, so this would be a induced random partition model. That's the jargon I've been using lately. And it typically has one interesting property, which may be useful for predictions and things like that, which is the sample size consistency. That means the model for n arises from the model for n+1 after marginalizing the last index. All right. Okay, so many of these non-parametric creatures, let's call them creatures, can be described by using this function. It's the EPPF, the exchangeable partition probability function. Here is spelled out. And this function satisfies a certain number of conditions. But basically, disregarding all that technical description for a minute, I guess all you need to define a random partition model is simply the expression for the EPPF. And that expression is a function of cluster sizes over here. So the probability of your partition being exactly this collection of subsets is given by the EPPF evaluated at the cluster sizes corresponding to those subsets. Of course, the EPPF it's deeply connected to combinatorial structures related to BMP models, and there's been great discussions on that. Igor gave a discussion on that a few days ago here in this conference. But anyway, the EPPF is one interesting property of these BMP models. Okay, now one thing here is that the EPPF might not necessarily be always available in explicit form. That means a formula that you can evaluate. There are a few exceptions, of course. The DP, the directed process that we all know about by now, I guess, or most of us know, is has an EPPF that can be written in this particular form. Another example would be the Pittman-York process, or sometimes it is referred as the 2-parameter DP. And it has this expression over here for the EPPF, and with some combinatorial, these combinatorial quantities over here. And you notice that if the alpha parameter is set to 0, then this formula reduces down to the DP. All right. And there are other, of course, cases where you can evaluate this EPPF explicitly. I guess I can direct you to these papers by Niedin and Pittman and de Blasi, Pierpaolo, and other co-authors that describe these things. All right. From the predictive viewpoint, which is something that I think it's interesting to look at, particularly if you're going to work with these things in practice, the EPPF induces this prediction probability function, the PPF, by simply computing the ratio of these EPPFs, where in the numerator you have the original collection of cluster sizes that you currently have, enlarged by 1 and divided by the EPPF evaluated the current situation. So this is like a predicted probability, and for the Pittman-York process you get something like this. So that allows to give some interpretations to this parameter. It's typically called the discount parameter. And if you set alpha to 0, you get the Chinese restaurant process, which it's been studied in this paper by Blackwell and McQueen, and many others have used that. All right, so that would be the BMP connection. I repeat, this is the way I came to this particular word, but then I found that there is an alternative way of defining these models, and it's a natural one. You just write down a formula for this probability. Of course, if you write down any arbitrary formula, you might not have any notion of sample size consistency. There is no guarantee that any arbitrary formula would be an ePPF, and actually the ePPF, I guess I overlooked that, but it has to have a certain number of conditions, and this condition guarantees that it will have this sample size consistency property. All right, so writing down a formula might give you an idea of what this joint distribution for your partition will be, but of course, there is no guarantee that you will get something that makes sense from the predictive viewpoint. And by that, I mean that the model for n+1 might not generate the model for n. So if that is an issue, of course, you have to be careful about that. But in any case, an interesting class of models is these product partition models. The product partition models have basically a very similar hierarchical structure to what I mentioned earlier, but now there is a formula for the random partition, which is proportional to this product of quantities, and these quantities are called the cohesions, and the cohesions are supposed to tell you how strongly one believes the elements on this particular subset are to co-cluster a priori, all right, before observing anything. And again, we can use cluster membership indicators to define this the partition in an alternative way. So you will have a model that is defined for these cluster memberships. And that's it. So that would be a model. By the way, here is the proportionality constant. So, and the proportionality constant, you have to divide by that. All right. So if you think in terms of how to define these models, well, you know, there is basically no limitation. All you are required to do is to provide an expression for this, which is supposed to be non-negative. You could even have some of these equal to 0 if you want, if for some reason you think that some of these subsets are impossible to occur. But in any case, since there are many such subsets, one wonders what exactly would be a reasonable way to define those. Well, one famous example is when you use this formula, and this formula gives you exactly the same ePPF, or the same expression, the same formula we had earlier for the DP. And actually discovering this was one of the things that drove me into this particular world now of random partition models, because I said, wow, there's a connection here. I don't think I discovered it. I just, you know, stumbled upon it, I guess, in some sense. But I've been using this as a connection between these two words ever since. In any case, a limitation possibly of the PPMs, of the product partition models, is that not any formula for C of S for this cohesion expression will give you a valid ePPF. All right. So another, I'm going to say this kind of quick. Another way of doing things in this clustering particular conception of creating partitions is to use mixture models, finite mixture models. And many people in this conference, there was a session where Sylvia Frubich-Natter was describing what happens with partitions in this context. Miller and Harrison have this formula for the ePPF in the case of a model with a prior on the number of components. And again, there is a a closed form expression here that you can use. All right. Of course, there's been extensions in of these models. One of them that has been used quite a bit is the partitions in blocks of consecutive indices, which is very suitable for things like change point models. And there is again a work by Baron Hartigan along those lines. And Rosangela Losky is one of the experts that's been doing work on that for quite a bit by now. And then there is partitions for more than one subpopulation. And here we get into all sorts of interesting combinatorial structures, and describing some of these things can be a little bit involved. Sometimes you require what is called the partially exchangeable, the PEPPF that describes how these things behave. And there's a very nice paper by Federico Camerlengi and co-authors describing these things, particularly in the context of what they call the latent nested mixtures. There is a paper by Mario Beraja and Alessandra, and that I will mention briefly in a few minutes, that also has to do with this. And there is also the connection that comes from what is being described as the dependent BMP models. The dependent BMP models come from the idea of this non-parametric regression. So how to construct a class of random measures that are indexed by a certain subset of covariates. And this seminal work by Steve McAkern in a technical report and a proceedings paper. I can't remember which is which, but those must be one of the most cited technical reports and proceeding papers that I've ever seen. And so the idea here is can be taken literally to induce random partition models that are now indexed by this covariate. So we'll get to random partition models again, but in a flavor that is connected to this non-parametric regression. And one of the papers that I actually had most fun writing was this with Peter Mueller and Gary Rosner on how to take the product partition models and put covariate dependence in there. So now that the prior, recall before the PPM had this product of these terms of the cohesion functions, but now there's this other term that we call the similarity function that measures the homogeneity of the covariate subset that are attached to that particular cluster. And the idea is that before observing anything else, if you have two individuals with similar covariate values, those are a priori more likely to cluster than two individuals that have covariates that are kind of like at the opposite sides of the space. That's the idea. And one particular specification, there are technical reasons behind this, but for pragmatically, we can think this is for convenience. One convenient way of doing this is when we express the result of the similarity function as if we were assuming that the covariate values are sampled from some model. Of course, we're not incorporating this particular Q into our probability model. This is just a way of getting a nice formula, a formula that can be evaluated, all right? So if in this auxiliary model, this is a likelihood that is conjugate with a prior, then we get something that can evaluate analytically, and that it's actually something that you can do very easily. So the Qs here are just for simple calculus, but in principle, any formula here will work with any formula that achieves the condition that closer values of the X's give you higher value of the G. When you have several covariates, you can play the same trick and simply multiply together all these similarity functions. And we have used that in a variety of contexts with covariates that are continuous, that are categorical, and even georeferenced coordinates, like in this paper that was published a while ago in Bayesian analysis with my friend Garrett Page. All right, so this is it turns out to be a very flexible alternative, and it's very good for prediction. That we have, one of the things that we have tried hard here is to do predictions in various contexts, and this model seems to work very well in these various contexts. Okay, so of course there are many other alternatives. I will just describe briefly a few of these alternatives. So this is a variation of the PPM, and by the way, we call this PPM X, the PPM with an X for covariates for covariate dependence. So there is a variation of the PPMX where you can take more general functions of the cohesions and the covariates that are part of that particular cluster, and that was done by Park and David Danson a while ago. There are other alternatives where you have this distance-dependent Chinese restaurant in a paper by Bly and Frazier. David Dahl has kept doing very good work on this area. So he has this cluster assignment according to the Pittman-York process, but now internally you can reaccommodate units according to a certain distance among the covariates. And there is an interesting sort of like a location scale random partition model that is proposed in this paper by Smith and Allenby. There is a very interesting construction by Sally Paganin and Amy Herring, David Danson, and some other co-authors, I can remember right now, where they have this centering process. And what that means is that you come up with some idea or you have some prior information what a suitable partition would be for your units. And then you build a ePPF evaluated at that center partition. And then you essentially allow for some deviations of that using some distance and some penalty parameter psi over here in this fashion, all right? So Sally gave ISBA webinar a while ago when she described these things. I think last Monday, David also gave a talk on what he called the shrinkage partitions distributions, where you can sort of like combine this idea with his construction of how to construct partitions using allocations that are based on distance. All right, so let me just talk about okay, so I have to hurry a little bit. So at first, I would say like a natural application of these random partition models is the clustering. So, and that simply comes from noting that a prior on the collection of all partitions implies a posterior on the collection of all partitions. And so a natural question is to say how can we use that model to estimate a partition? Well, estimating a partition is like selecting one individual in this huge, potentially huge collection of partitions. So this is not an easy problem, how to single out one element there, all right? So excluding just purely algorithmic options, there are several possible solutions that have been proposed. And you will see that David Dahl features prominently in all this list because he's one of the persons who's been doing most work on that. So there is the model clustering paper that David came up with a while ago. There is loss function approach, and Binder is proposed a loss function that has to do with misclassifications. There is the least square clustering, and there is Lau and Green that took over this Binder function. There is work by Sarah Wade and Garamani on point estimates and credible balls. And actually, I think David has a paper on the Journal of Statistical Software, and there is a package that implements a number of options. And there is another work that is coming up soon, I guess, where David and Peter and others do more evaluations of these things. Basically, so how to construct partitions based on posterior summaries. All right, so let me just move to one quick application. So this is something that was published a while ago, 2015 in Bayesian analysis. So the idea is to consider data that measures, it's actually this Hollinger game score that is, it's a constructed measure of performance for basketball players. So we have here, like all of these are the measurements, these dots in these plots. So here is a subset of 3 of these basketball players. And what we can see here is some, kind of like a smoothing of this cloud of points. So the problem here is, or one of the problems that we tried to achieve in this paper was to the following. So how can we construct a partition of how can we group these players according to this cloud of points? So basically, what we came up with is player-specific curves. But then if you look at these player-specific curves, you'll see that there may be lots of particularities here, like subtle variations and ups and downs that, depending on how you define this, the model for the curves, can actually lead to the conclusion that everyone is a singleton, because no two curves are literally alike. So the idea was to create what we call the cluster-specific curves, and those curves are driving the clusters. And within each clusters, we allowed all these players to have a little variation, so little, jitter, if you will, around this cluster-specific curve. And we did that using B-splines, which I think worked very fine, because then we didn't have to worry about transdimensional inference at the curve level. So we had like a number of nodes, of fixed nodes for each individual. Oh, there were other issues related to alignment, etc., but I won't go through that. And so we came up with a PPMX model that took into account the age, the experience, and draft order for each of these players to construct the clusters. And this is a summary of, I think it's the 9 most, the most numerous clusters, so the most populous ones. And you can see here we wrote some of the prominent players that were assigned to each of these clusters. So you see LeBron James over here, you see Shaquille O'Neal over there, Kobe Bryant. And so using that, we can, of course, present a certain description of what the data looks like and how these clusters, what these clusters mean. But then you see something here. I think there's in total, if my memory serves right, there's a total of 18 clusters. These are 9 of them. And you can see that some of these forms in the curves are not really super different among each other. There might be some differences in where the curves are placed, like the height on this axis. But the curves are, the clusters are not super different. So which actually led to work that has to do with repulsion. I will explain that now. So in this context, and Garrett gave a very nice talk on this on Monday, I think. So you can look it up because it must be recorded. So the one thing that typically happens when you estimate clusters, especially when you use things like the DP or PPMs with the cohesion formula that is related to the DP, is that oftentimes you will find very small clusters or even singletons, which are, of course, very difficult to interpret. And one of the reasons that is being created is because the cluster-specific parameters are typically assumed to be IID from a certain, baseline distribution, oftentimes as chosen by convenience. But since they're IID, they are actually they're not restricted to be separated, or they can be actually anywhere. And of course, they will tend to concentrate in areas where most of the mass is being assigned by this Bayesian distribution. So one possible solution to control that, and control that means trying to avoid the idea of having these singletons, or even trying to reduce the number of subsets that you want to estimate, is to incorporate the idea of repulsion. Repulsion basically refers to a model that incentivates the different individuals or the different points that you are considering in this collection to be separated with high probability. So that should be some kind of penalty for points that are coming very close to each other. All right, and so that would be a solution because the prior will try to control that. All right. So and Garrett gave a very nice talk on one particular way that we did that. I will just try to describe this with a picture. So here is some simulated data set. Garrett showed some other type of data, of course, but so here is a mixture of 4 normals that I simulated using 4 not super separated means and some variances that imply some degree of overlap. So this is the original data. The colors identify the clusters. On the right-hand side, what I did here is to fit a DPM mixture and come up with the least square clustering that is available through one of David's packages. And here we see what exactly I was referring to earlier. So you see 6 clusters compared to the original 4, but now the 6 clusters include this funny and isolated individual over here. So this is a singleton. And that's exactly the problem I'm referring to. So through this repulsive model that is described in this paper by Jose Quinlan, a former student Garrett, and myself, published recently in early this year, actually. So we have the same data over here in the left, but in the right, we have this repulsive model, and the repulsive model has 2 components. It has the product of independent normals and something that puts a penalty on proximity. All right. So using that, now we came up with 5 clusters, still not the 4. But you see here, there is no singletons anymore. So the funny observation that was isolated here in using the DPM is now absorbed into this other cluster. And the 6 clusters that were reported with the DPM now reduced to 5. So that's one of the things that we are actually trying to do. So we're currently, this is kind of like a project in progress. So we want to take more complicated curves and apply a repulsive model so that we can kind of like make more stylized clusters and probably reduce the number of them. Okay, so now that will be kind of like the background and introduction. So I'm going to move into more recent applications that I've been working with. And this is a paper with Mario Baraja and Alessandra on clustering subpopulations. So a random partition model can be applied to essentially any type of structure. So it doesn't have to be points, you know, in some space. It can be something much more general. And what we did here is to carry this idea to the context of distributions. Distributions or subpopulations. So I guess the beginning of the question, the beginning of this project was the question of exchangeability versus partial exchangeability. So exchangeability means that you have a collection of separate subpopulations, and they are all coming from essentially the same distribution. So you could permute the individuals in all these different subpopulations, and the joint distribution would be the same. And partial exchangeability would mean that the opposite of exchangeability, which means not every permutation of this complete collection of objects have the same distribution, the same probability. All right, but then and of course there is a lot of work that has been around this particular topic. So how to contrast subpopulations. But then we came up with the following angle at these problems. So if you ask the question, are these subpopulations exchangeable? There are, of course, two answers. No, yes. If yes, problem finished. Things are exchangeable, nothing else to say. So all these subpopulations, or all the distributions described in the subpopulations are the same. But if the answer is no, why? So if you have only 2, of course, that means that the distributions are different. But if you have 3, 4, 5, 10, 100, what else can you say? Could you actually determine subsets that are internally exchangeable or not? So that was the motivation behind this project. And Mario has a recorded video on this also, available on this conference. So the semi-hierarchical data process allows for such cluster analysis. And our model here is the following. So there, it's a hierarchical model, of course. So on top of everything is a flexible mixture. So there is a total of if you have capital I subpopulations, there is a total of capital I possible distributions that you have to use. And potentially, there would be one different for each one if you're in the most extreme case, or they all coalesce to a same single individual if you're in the exchangeable case. But at any rate, you allow the data coming of the measurements coming from each of these subpopulations to have this flexible, mixture model with a CI here that indicates to which of these, starting distributions that you come up with, each of these subpopulations will be attached to. All right. So this is the CI is what allows selecting the possible subset, and then there is a random partition model. You could take anything here. In practice, what we did is to use a simple mixture model, a finite mixture model with capital I possible components. So this is just like a multinomial thing. And so these two, this gives you the flexible approach, and this gives you the possibility of choosing where you are going to be assigned to. And then the semi-hierarchical HDP allows for several things. It allows for populations or distributions that share things, but not necessarily degenerate into exchangeable cases. There is a common atom in different subgroups. This is one of the things that motivated, by the way, Federico Camerlengi and others, and Igor and Antonio, and I think David and Abel, to come up with alternatives to the nested DP, because the nested DP suffers from that problem. And this is our alternative proposal. So you can see that each of these FIs over here has a flexible mixture representation, like an infinite mixture representation with the weights coming from some stick breaking construction, and the atoms being drawn from another mixture between a DP, which is the G tilde over here, and G naught, which is some non-atomic measure. And there are several properties that are studied in the paper. I'm not going to go through them, but essentially all I want to stress here is the clustering part. So the clustering part means that if you have 4 possible subpopulations, and this is the particular assignment of this subpopulation to clusters, you're essentially saying that F4 will never be employed. F1 and it is used twice for subpopulations 1 and 4, and then F2 and F3 are assigned to subpopulations 2 and 3. So we apply this. I don't really have any time for describing or discussing computation issues, but we apply this construction to a subset of data that was actually taken from my own university. So I have some colleagues who teach this, several sections of this second course of calculus, which is taken by a variety of students. So the students here are 161 in total, and they are divided into 3 parallel sections. The division here is typically by preference. Students have their preference in terms of schedules, etc., etc. But I mean, beyond that, there is a lot of randomness in this process. And also, what they do normally is to have everything coordinated in such a way that there are is the same course material, so essentially the same material is being taught in all these sections. The exams are in common, the graders are shared across all sections, so everything is pretty much the same except for the instructors, okay? So as a way of evaluating instructor effectiveness, and here I want to stress that we're not doing any sort of causal thing here. We just want to compare these subpopulations and see if there is any role played by the instructor in how these students perform at the end of the course. So I have to say something a little bit because this is kind of funny, because in my country, we use a grade system that goes between 1 and 7. I have no clue why it's like that, but I mean, it is what it is. So we're used to it. And grades typically have 1 decimal place. Because of that, we added a little bit of noise to each of the observations to avoid, repetitions, ties across the observations, and then standardized all data to treat them as continuous. And this is just out of convenience. So A, B, and C denote here sections 1, 2, and 3, and the YIJs are the grades of each of the students within each section. I don't remember very well the sample sizes between each of the sections, but in any case, so here is the estimated distribution for section A, B, and C. So these 3 plots over here describe that. You can see that B looks a little different from A and C, and A and C look kind of similar. So, this is our density estimation describing the performance of the students. But on the right here, I have a histogram showing the top 3 clusters in terms of the posterior probability. You see that the highest posterior probability goes to the subset 1, 3, the partition that has subset 1 and 3 together and 2 separate. So that means the most likely partition attached to these 3 sections would be joining A and C and separate from B. Okay, but also there is a considerably high probability to everyone being separate, but this one has a slightly higher probability, so that's that would be our conclusion. There is a smaller option here of joining 2 and 3 separate from 1. But in any case, that's the kind of analysis that is allowed. We also look at some posterior summaries of this. So we can look at the mean and variance in this fashion. We can look at the skewness coefficient for each subpopulation, the Arnold and Grunwald measure of skewness around the mode, and the probability of passing. Oh, I didn't say that, but in our system, getting a 4.0 means passing. Anything 4.0 or higher means passing, and anything less than that means that you fail. All right. So it would seem here that the distribution for the section B has the data or the students in section B have higher probability of passing that students from A and C. And then I guess I don't really have much of an explanation for it. I know who these people are. They're my friends and colleagues. I won't say anything, of course, but I guess you can sort of like think in terms of pedagogical abilities of each of the instructors, favoring a certain collection for students, but there is lots of randomness attached to this thing. So anyway, so I will just quickly, these are some pairwise joint distributions that, A and C look very kind of similar, A and B look kind of different over here. Same thing with B and C, but A and C kind of looks not so different. All right. So very quickly, variable dimension regressions. I guess.
Fernando,
yes.
This is Mike. Let me jump in. It's a good point. We got just over 5 minutes left.
Okay, perfect. Thank you. I'll try to rush this, and I totally skipped the last project. So variable dimension regression. The idea here is to deal with missing observations. Missing observations, of course, very popular, very, very common to find. The typical analysis includes some kind of complete case, which means drop whatever is not complete. I'm guilty as charged. I'm not claiming this is, I'm not condemning that, but I'm just saying what it is, okay? All right, so most of the cases, you deal with incomplete responses, but of course there is much less attention given to the case of missing covariates. And this is what we call the regression with variable dimension covariates vectors, because all these vectors have different number of valid observations attached to it. All right. I guess I don't have much time to go on discussion, but there are a number of references typically connected to variations of this multiple imputation by chain equations, the mice algorithm. So I guess I'll just leave it at that. So our main interest here is to come up with a flexible model that allows imputation, that deals with the problems of missing observation and has good predictive properties, all right? And the main idea, and I can say it in just like that, no imputation, okay? So whenever there is something missing, you simply skip it over and don't use it. That's it, all right? I guess I will skip this complicated notation, but basically the idea is that when you evaluate the similarity function, if you recall, this flexible way that we, this practical way that we came up with using auxiliary models, you basically, it's kind of like the marginal distribution under some IID auxiliary model that is not used in our model, but it's just a mechanism to get easy calculus. So whenever you have something that is not observed, you simply skip it. Don't use it. That's it. No imputation at all. All right. And this is just was meant to show that you essentially have something that we call the locally weighted regression when you examine predictions, because you will be considering individuals trying to match these covariate values for the new individual with whatever you have. So I guess this would be a way to show that. So this would be the predictive regression for a new individual. If you have the two, in this case, two covariates x1, x2 available, you will get kind of like a surface response that looks like this. But if you only have one of them, let's say x1 is available, x2 is missing, then essentially you have something that moves along the x1 direction, but it's fixed at x2 because you don't use it. And if you don't have anything, you essentially have a point. All right, so that's the idea. There's some data set that is publicly available that we used to try these things. So basically we did fits and predictions. So these are, I guess it shows the percentage of missingness for each of these predictors. So these are repeated observations at 9 a.m., noon, and 3 p.m. of temperature, nebulosity, and projection of wind. All right, and these are the missingness patterns over here. So you see there is quite a bit of missingness and all sorts of combinations of what is missing and what's available. And so we compared our model here is in the left of fits and mean square error and mean square predictive error. So we compared against a BART-based procedure, the multiple imputation and the pattern submodels, and we actually performed very well compared to those methods. And I guess I will simply skip all over that. I was going to tell you about what finding interaction means, but for the sake of time, I will skip it. So my final words. In my view, these random partition models are deeply connected to some classes of Bayesian nonparametric models. Not all of them, of course, but many of the ones that people use have this discreteness property, and that's exactly what brings the random partition model into play. Many such models have good predictive properties, and I've been using this PPMX construction, and we have tried it in many different scenarios. So that is something that I think we have tried in practice, and it has very good predictions. And of course, there are many applications that are there out there to be developed. We have used in a few also on our own. And again, there are, these random partition models. I guess the reason why I like them is that because they are very versatile in capturing heterogeneity in your sample. And since they can be combined with many types of hierarchical structures, likelihood models, etc., and you can build such a complicated a model that is as complicated as you wish, in a sense, the sky is the limit. One little subtlety I would like to stress is that when you define things directly using a formula, you typically get a little bit more control as opposed to the induced models that come from, essentially bringing into place the ePPFs and building things on a non-parametric distributions. All right, but of course, the things like the sample size consistency are not generally obtained. So anyway, so that's what I wanted to say. Again, thank you very much for your time. And again, if I am here, it's because I have good friends and collaborators. So that's what I want to stress. I would like to be with you, but next lifetime, as Peter Mueller says. Thank you.
Well, thank you, Fernando. In my opinion, an exemplar foundational lecture, reflecting on the core foundations and then bringing us up to speed on more recent developments, growing from those foundations. Let's move to some questions. Let me see. What do we have here? I think I can let people speak, and I would like to. So let's go to Ed George. Ed, you can speak, I think.
Can you hear me?
We can, yes.
Oh, wonderful. Fernando, that was absolutely splendid. I hope you'll make the slides available. It's just terrific. My question was in clustering the A, B, and C, which was terrific, but suppose you had additional covariate information on the students. Does that make a difference? Maybe the students in one section are a lot younger than the others, something like that.
Yeah, absolutely. I mean, this is a great question. We didn't have any additional information on this one. A lot of these had to be anonymized for, privacy disclosure reasons. So I had to actually go and beg my coordinator, my teaching coordinator, to let me use this data. But we could incorporate that information in many different ways. Like we could build a regression on top of everything and still have something that connects these distributions in such a way that we could cluster them. So we would be clustering something that is, in a sense, corrected by the covariates, by the whatever information that's available. But in this particular case, we didn't have any further information that we could use, because that would, open some, kind of worms in terms of privacy disclosure.
Wonderful. Thank you.
You're welcome. Yeah, so by the way, I asked, how can I make these slides available?
Fernando, that's okay. It's being recorded, and ISBA deal with that. Let's just wait. Let's see if there, give the time. Let's see if there are more questions. So on that point, the foundational lectures are recorded. They'll be available, I understand, for several months, and the slides will be there. And then I'll leave it to ISBA to deal with the speakers in terms of people want hard copies. Any more questions before I jump in with a question? We've got just a couple of minutes. Well, let me waste the last 90 seconds, Fernando, with a couple of points. Lovely talk, as I say. Back to the start in terms of covariate dependent partition models. Mm-hmm. You did a lot of good things, and then you talked about examples, but one of the general areas you didn't really touch on is time-varying partition models. Way back 12 or 13 years ago, we were very involved in this, as were many other people, in extending the Dirichlet process-based partition models to context, and this was connected to systems biology applications, where cluster sizes would evolve, cluster membership would evolve, and the partition theory didn't evolve as fast as we needed. A second related point is that of theoretical development that's really focused on things like cluster size and subcluster size, as opposed to other questions that are often of, more practical, goal-oriented interests, such as let's look at, what can we say about the smallest 5 clusters, and co-clustering of membership, beyond bipartite, like what's the probability that these 17 cases lie in the same cluster? So most of the theory is focused on sort of what I guess more aggregate level questions rather than more focused applied questions. So I'm just probing about, for leads on, it's an area I've moved out of in the last decade, but I think a lot of people here today, would be interested in how contacting specific applied interests is influencing the theory and the foundations.
Okay, great questions. Regarding the first one, we actually have a separate work with Garrett Page again and David Dahl, where we have constructed a model that exactly is for the situation that you described, a sequence of partitions that evolve on time. And the way we did it is to come up with what we call the pegging indicator. So something that is pegged is something that won't move next time, and something that is not pegged is up for relocation next time. Might end up in the same place or not, but that's up to chance. And so one of the reasons why I said that coming up with a formula is more flexible than having things induced in terms of random measures is that there are several works that define a sequence of random measures and connect them in some way, and then use the discreteness property of these objects, these random measures, to construct a partition. In doing so, we actually verify that certain classes of models, and there is a very nice work by François Caron and co-authors doing that, the sort of correlation they allow in terms of these partitions is way smaller, but depends up to certain parameters, of course, but this is smaller that you can achieve by this trick of defining the pegging indicators. The correlation that we get is actually up to 1, all the way up to 1. Could be even, from 0 up to 1. For these other models, is limited by a certain quantity that can be computed in principle. So there is work we have done on that. And there is a paper that is in the latest stage of submission and revision right now. I could have, chosen that, but I did not for chance. If I had known, I would have, done that.
Right. Let me jump in there, Fernando. Thanks.
Yeah.
And I think some people might want to follow up on some of these leads. We're right at time, and the webinar is about to end. I think in the normal course of things, in my experience, the last 3 days, the Zoom session stays live a little bit. So I will hang on in case it does, and in case other people want to spend a few more minutes chatting with you. But the formal session is about to close. Okay. So thanks again for an exemplar foundational lecture. Wonderful choice this year. And I hope and expect that our substantial audience here will agree with me. Let's all congratulate Fernando once more and thank him for a stimulating talk.
Thank you. Thank you. And thanks to my co-authors, my friends. I'd like to see you. So